So before I even look at the questions, the first thing that I notice that annoys me is it says at the top, g equals 9.8 metres per second squared. So anything in metres per second squared must be an acceleration. So that's telling you the acceleration due to gravity. So that's the acceleration that something will have if there aren't any forces on it apart from its own weight. Now when we glance at these questions, we see there's all sorts of forces that are either given or that we're looking for. So in none of those questions is the only force the weight. So in none of these questions does anything ever accelerate at 9.8 metres per second squared. And one of the questions is about a lift. If you were in a lift and it was accelerating at 9.8 metres per second squared, you've got some problems coming because it means that the cable's snapped. So I think that to give the acceleration due to gravity is to involve extra confusion because it gets you thinking about the acceleration something would have if it didn't have the acceleration that it's got in the question. Because there is a good reason why it's had to give you the information about 9.8, and that's because a mass of 1 kilogram has a weight of 9.8 newtons. That's the information we're going to be using. So really, if I was writing the question, I wouldn't have said the acceleration due to gravity is 9.8 metres per second squared. I would have said the gravitational field strength is 9.8 newtons per kilogram. And because I can, I'm going to cross that out and I'm going to write newtons per kilogram. Metres per second squared wasn't wrong, but it's not the useful weight of the information. No need for you to go defacing your books though. And in fact, if we just look back to the previous page of the same book, for these questions, it said G was 9.8, it actually even put a different value, it said 9.81 newtons per kilogram. So yeah, that's done with dissing the bloke who wrote the book. Now let's get on with answering the question. So question 1, it says you got a rocket. It says the mass of the rocket, it says it's blasting vertically, and it says what the acceleration of the rocket is. So the rocket is accelerating at 4.2 metres per second squared, and obviously that acceleration must be upwards. Because if it was accelerating downwards, it wouldn't get off the pan, it would go through the earth. The first thing we're asked for is the weight of the rocket. Now the weight of the rocket, that just means how big's the force that the earth pulls the rocket with. So it's got nothing to do with what the engines are doing. It's got nothing to do with whether the rocket is accelerating or not. It's simply a case of, you know the mass of the rocket, you know how strong the Earth's gravitational field is, so you can find the weight. And that's where we need the information that was given at the top of the question. And that's why I wanted to change the units, so it's newtons per kilogram. So part A, you're going to get the weight of the rocket in newtons, which has got nothing to do with whether or not the rocket's accelerating. For part B, it's asked you to find the thrust of the rocket engines. In other words, we can actually look, there's a picture over here in the example. There it shows a rocket. It shows the weight acting downwards, and it shows the thrust is the force pushing the rocket upwards. The fact it's drawn the arrow above the rocket, that doesn't matter. All we're interested in is the fact that there's an upwards force. It's obviously coming from down below where the engines are, but it's an upwards force pushing the rocket upwards. So how do we find the thrust? Well, we have to remember that when we use the equation F equals ma, in that equation what is F? And the answer is that F is the resultant force. So since the acceleration is upwards, we're going to want the resultant force upwards. So we have to think, we've got the thrust pushing upwards, and we've got the weight pulling downwards. How do you find the resultant of an upwards force and a downwards force? And then you do that in symbols. So T is the thrust. The weight we can call W. What's the resultant of T upwards and W downwards? You find their resultant. Once you've found their resultant, that's going to be equal to ma. And since we know the mass, and we know the acceleration, and we know the weight, we should be able to find the thrust. And just as a check, we know that the thrust must be bigger than the weight, because if it wasn't, the rocket wouldn't accelerate off the launch pad. For question 2, the first thing we're asked to find is the tension in the tow bar. Now, of course, the tension is just a pulling force. So what we're looking for is the force that's pulling the trailer forward. It says that we can ignore air resistance. So the force from the tow bar is the only force that's affecting the trailer. Now, we know the mass of the trailer. We're trying to find the force. So what links mass and force? And the answer is that force equals mass times acceleration. So we need to find the acceleration of the trailer. Well, because the trailer's stuck to the car, the acceleration of the trailer has got to be the same as the acceleration of the car. And the question doesn't tell you the acceleration, but it gives you all the information to find acceleration using SUVAT. It tells you it starts at rest, it speeds up to 9 meters per second, and it takes 60 seconds to do it. So using SUVAT you find acceleration. Once you've got the acceleration, and you know the mass of the trailer, you can find the force that's causing it to have that acceleration. In other words, you can find the tension. For part B, to find the engine force, the simplest way is to say, what's that engine force doing? Well, we're ignoring any effects of air resistance. It doesn't have to overcome air resistance. All the engine force is doing is making the car and trailer together accelerate. And you know how much acceleration they've got, and you know how much mass they've got altogether. So it should be easy to find the engine force.